Hey, Ruben.
Hi, everyone.
What?
How you doing?
Is this our last session
That is the last session of the day. It's the lucky
of the
last
conference?
session.
Lucky last.
Yes,
What a
last but
privilege.
not least.
Yes, last but not least.
Alrighty,
Well,
so
let's see.
we are going to be talking about supercharging your cloud applications with Orleans.
I was gonna say, let's bring this PowerPoint up.
I'm going to bring your PowerPoint up here.
Mhm.
All right, take it away.
Great. Thanks. Yeah, so as Jamie mentioned, we're going to be talking about how to supercharge your cloud-based applications using Microsoft Orleans. I'm Ruben Bond. I am an engineer on the Orleans team at Microsoft. You can see my Twitter handle here. It's at Ruben Bond. And the Microsoft Orleans Twitter handle is down here at MSFT Orleans. Okay, so let's imagine that we're building a web app. And we want to keep things simple, so we start with a pretty traditional kind of an architecture where we've got the internet talking to a load balancer, talking to a bunch of servers, which end up talking to your database. And you might notice that we've got a few different servers here. And the reasons for this are twofold. One of the reasons is that we imagine that this is a popular application, and so we need to be able to scale out in order to be able to support a lot of requests concurrently, so we can support more requests by adding more servers. But the other reason, perhaps more important, is that we also want redundancy. So in case one of these servers crashes, the load balancer should be able to route around that crashed server and send requests to these remaining servers. So a typical kind of a request flow in this case is going to be that a request comes in off the internet, the load balancer will send it to a server. Your application is probably running something like ASP.NET, so it's getting handled by a controller in there. And then that request is probably going to go and call into the database, read some data. Perhaps it's going to modify some data in memory, write the data back into the database, and return some response back up to the original caller. So that does work pretty well. But there are a couple of problems with it. For one, there's this problem of slow access. So anytime a request has to make another hop across the network and go to the database, that adds up, it takes time. And so if you're doing 2 requests to the database, one for read, one for write, on every single request, that's putting a lot of undue read load on the database, and it's adding extra latency for network hops. Ideally, we want this database to be freed up to be able to serve mostly write requests and not have to waste its time with read requests that we could serve potentially out of memory. Another issue, which is potentially more nefarious, is write contention. And so to illustrate what write contention is, imagine that you have a request that comes in, and this app server over here wants to go and update some row in the database. And so it issues a request to the database. But at the same time, concurrently, there's another request that arrives on this server over here. And it also wants to update the same row or the same object in the database. Now, something needs to happen. We want our application to be consistent. So we have to make sure that these requests don't clobber each other. We might use, say, database transactions to ensure that that doesn't happen, so that we queue one request after the other in a transaction, and that adds a little bit of latency to the subsequent requests. Or we could use something like optimistic concurrency control, where we have e-tags and we do a check to make sure that the data hasn't been updated since the last time we read it. And in that kind of case, you might have the application do a retry in case the data has actually changed underneath the hood. But in both cases, you're putting a lot of load on the database or in the application. Anytime you issue a request and it has to be retried because there was an issue or it's queued up behind something else, that's unnecessary latency, and that's something which the client might end up having to see. All right, so let's tackle this first problem of slow access. A common kind of way of tackling this is to add a cache. And so now, when you want to serve a request, you're going to go and read from the cache. If it's there, then great, you modify it and update it. But if it's not there, then you read from the database. So you've got this kind of dual read approach, read from here, fall back to there. And then you're going to update it in memory potentially, and then you've got a dual write it back to the cache, back to the database. So that's good. That actually works pretty well if you've got things like, let's say, blog posts or articles that don't tend to update very often. But otherwise, it does introduce some problems of its own. So now that we've got a cache, we have to deal with one of those famous 2 hard problems in computer science. Namely, those are the problems of cache invalidation, naming things, and off by 1 errors. And so by adding a cache, we've got this cache invalidation, cache coherency issue. Also, we haven't done anything to solve the write contention problem that I mentioned before. In fact, now we have to do our writes both into 2 different locations, and so it's even more difficult to manage. And we've also got complexity. We've got complexity of infrastructure, but we've also got complexity of application code because we need to manage some code to do this dance in our application. Okay, so let's try to handle this write contention problem. A typical kind of solution to this might be to add in a worker queue. And so anytime some request comes in that needs to issue a write, you're going to push a message onto this queue, a job, so to speak, and that's going to get pulled off by a worker. Maybe that worker just sits in the applications. And that's going to issue that, it's going to handle that request, it's going to update the cache in the database, and effectively serve that work. And this can eliminate write contention if you, say, partition your system so that you've got each of these instances serving an equal number or an equal amount of the address space. But all in all, this still has problems. You've still got these caching issues, but now you also have this slow asynchronous writes because now anytime you issue a write, it has to go through the queue, get pulled off, get processed, and all the while, the client is still waiting for a response. And so they might have to use something like long polling. So polling, is it done, is it done, is it done? Or maybe some side channel to get notified when this work gets completed to see if it's successful or not. So we still have problems, and we have a lot of complexity, a lot of application code complexity, a lot of infrastructure complexity. Now, part of the problem here is that we're treating symptoms. We're not really treating the root cause. So if we think about how could we fix this, if we think in a more sort of fundamental sense, we can fix this by adding in some coordination. You know, if we coordinate between our different servers by having some kind of communication, then maybe we can have a programming model that allows us to avoid these write conflicts, avoid these caching problems, and alleviate pressure from the database, all the while being fault tolerant, very scalable, and simple. It's simple code. So hopefully today I can convince you that Orleans gives you all of this. So what is Orleans? Orleans is a framework that we built at Microsoft for building stateful cloud-based applications using .NET. And the core building block in Orleans is something called a grain. You can think of them like cloud-native objects. These grains communicate using interface calls, asynchronous interface calls, just like gRPC. So it's an RPC kind of paradigm. And when you're using Orleans, Orleans handles a lot of heavy lifting for you. So for example, Orleans will handle things like scale out and scale in. If you've got your application and it's under a lot of load, and so you want to add more servers, Orleans will start distributing more load onto those extra servers that you've added. And on the other hand, when you're scaling in and removing servers, Orleans will help to migrate the load back into the remaining servers. It's also fault tolerant, so it'll detect when one of these servers stops working for whatever reason and route around that damage. It handles service discovery for you transparently, so you don't have to think, I want to talk to this service, where does it live, and then go and communicate with it. Instead, in Orleans, you just say, I want to talk to this service, and you just talk to that service. We'll see how that looks in a moment. Orleans distributes load around the cluster, and it also handles things like messaging and routing. Now, we've been running Orleans in production at Microsoft for over 9 years now, and it's been adopted by many product groups as well as external users. Some of the product groups that you may be aware of include Azure Digital Twins, Halo, Microsoft Mesh, Dynamics 365 Fraud Protection, Azure Machine Learning, Azure Quantum, and Azure PlayFab. I talked about grains. Now, grains are this core building block in Orleans. You can think of them akin to what a controller is in ASP.NET or what a hub is in SignalR. They're really that core part of that programming model. Now with grains, the idea is that you divide your application up into many little objects. So you're going to have one grain activation, one grain instance for every user profile in your system, for every shopping cart in your system, game session, chat room, so on and so forth. And each one of these grains gets an ID. It's some kind of name that you can use for referring to that grain. It's backed by a class. It's just a regular .NET class, which inherits from this grain base class, and they can persist some state. So for example, if you think about a shopping cart, that shopping cart might have some state like the items that are in the shopping cart, for example, and that's associated with its grain. And so the grain mediates all of the writes to storage and reads from storage. And so you can avoid those write contention issues and those cache coherency issues because everything goes through that one grain. Orleans will distribute your grains across all of your servers for you, and it automatically loads them into memory the first time that they're needed. It also unloads them when they've become idle. So the first time that you need to access your shopping cart, Orleans will make sure it's there for you, and it'll load its state from storage before ever handling any requests. And it'll also, once it becomes idle, it'll unload it so they could free up memory for more things. It routes every single call for a given grain to the same instance. So any call for your shopping cart always goes to your shopping cart object. Say it's on server X, every call will always go to server X for that shopping cart. And they're also single threaded, and we do this simply for ease of use and to prevent a lot of bugs. So in your system built on Orleans, you scale by having a lot of grains. You don't necessarily need to scale any one individual grain. And so that results in less bugs. You don't need to use concurrency primitives. It's a lot easier, and it helps you to coordinate writes to storage. Okay, so that's the sort of high-level overview of Orleans and the theory. Let's get a little more concrete by building a voting application. And so this is going to be a web app that lets users create polls and then vote on them. And a poll it just consists of, it's very simple. It's a question plus a series of options that they can vote on. Here's what it looks like. So we've got a Blazor server web app called Grain Poll. And here's one of the, I think, 2 or 3 pages in this whole web app. It allows you to define a poll. You set the poll's question, the title. You can set a bunch of options there, click create, and that'll take you to the next screen where you can vote on one of those options that you've defined, and then also see these votes rolling in live. So you can see live updates of who's voting on what. Okay, so it's a simple kind of a web app. How do you build that using Orleans? Now, the simplest kind of approach is to just say, well, what if we had one grain for every single poll? And so what we're going to do is we'll generate a random ID, a random poll ID that we'll use to identify that poll with, and then we'll have one grain per poll. And that grain will just have 3 methods on it. One method to create the poll, one method to vote on the poll, and one method to get the results of the poll. And that poll grain is going to be responsible for reading and writing to its own storage. So it's the only thing that does that. So our Blazor web app, the front-end code, is just going to call these methods, call into the grain, and get the job done. So far, so good. That's great, actually. That will scale very well because you can add many, many, many polls. You can add many servers, and it'll scale practically linearly. But there's a problem. If we take this to the internet, the moment we do, we're going to start to get some misuse. We're going to have people who are voting on polls multiple times. We're going to have people who are creating thousands and thousands of polls. And we're going to have people flooding polls with many, many requests at once. And so we need some kind of an anti-misuse mechanism here. And so what I've done here is we've changed our design a little bit. We've still got the poll grain. We've still got the Blazor web app. But now we've added this new grain in the middle. I've called it a user agent grain. So it acts on behalf of the user. And the idea here is we're going to have one of these user agent grains per client. And we'll just key this one off of the client's IP address. So we've got a poll that's keyed off of some random poll ID. We've got a user agent grain, which is keyed off of the client's IP address. And you can see the methods here. The methods coming into the user agent grain are the same as the methods coming into the poll grain. Create, add votes, and get the results. So all the poll grain does is it does some bookkeeping to prevent misuse and then forwards the requests on to the requisite poll grain. Okay, let's have a look at how that actually looks, and then we can look at the code. So here's our Blazor web app running on localhost. You can see that first page, and we have some options here. We can define a poll. I'm just going to autofill it with what is your favorite color. And then I'm going to create the poll. I can vote on an option, say blue, no yellow. And this is the result. So it's a very basic web app. Obviously, I don't have very good web dev skills, but let's try some of these anti-misuse features. So let me try double voting. What this button does is it just sets the Blazor's status to pretend like I haven't voted, but it doesn't change anything in Orleans. And so let's say I voted for that before. I'm going to vote for this now. It prevents me from doing that. We'll have a look at this code in a moment. And I can also show you the live update of these results. So this is just randomly voting for these things. You can click it many times to get a lot of votes coming in. Okay, so that's the app. How does it look in code? What I've got here is this voting sample, and you can see this on our GitHub. And we're going to start by looking at program.cs. And so this starts off with a basic Blazor web app, a basic Blazor from the template. And I've added this code here to configure Orleans. So after installing the Orleans package, I just need to call use Orleans on the host builder here. And then I need to configure Orleans. And what I'm doing is I can configure it one of two ways. If we're in development mode, that means the host environment is development, then I can configure it to use local host clustering and in-memory storage. So these are some options which are good for if I just want to be able to hit F5 and get started. They're not suitable for production though. So if I'm in production, then maybe instead I want to do something like integrate with Kubernetes, and maybe I want to use Redis in order to be able to discover where my other servers are. Or maybe I want to use Redis to store all of this voting data. So I've configured this vote storage in both cases. Okay, so now we've added Orleans to our application. We can get started by adding and defining some grains. So I'm going to go to iPollGrain.cs. And here's the definition of that grain. You can ignore this stuff here, which is just for live updating. But looking at the rest of it, you can see that we define this poll grain interface. And we know it's a grain interface because it derives from this iGrain with string key. The string here is going to be that random poll ID that we generated. And it just has those three methods that we talked about. So it has one to create the poll, another to get the results, and another to add votes. And they mostly deal with this poll state type. It's got a string for the question, and then a list of the options with the corresponding votes on it. So that's our definition of a poll grain interface. What does the implementation look like? We'll go into pollgrain.cs, and we can see here. Now we know that this is a grain implementation because it inherits from this grain type here. It implements our iPollGrain interface as well. So Orleans knows that when someone wants the poll grain, iPollGrain, it needs to use this class. That's how it links them up. Okay, so you can also see the implementations of those methods that we defined on iPollGrain. But what I want you to look at first is the constructor. Now, our poll needs to be able to store its state durably so that if there's a server crash or some other kind of issue, we don't lose all of our state. And in Orleans, we can do that by injecting iPersistent state of t, where t is our state type. So before in program.cs, we defined that there was this state type called votes. So that's where we're going to store this stuff. It's going to associate that vote storage type with this state here. And so we set that on the class, and then we can use it. You can see where it's being used down here. The first thing I want you to look at is in the read method called getCurrentResults. All we need to do here is access the current state in memory. We don't need to load this state from storage because Orleans will make sure that that state is already loaded before we ever execute any of our grain methods. Writing or updating the state is similarly easy. So in this case, we take the state, this definition of our poll, from the create poll method, we set it on our state, and then we tell Orleans to please write this durably to storage. Now we know that in the dev case, when we're using in-memory storage, that's not actually durable, but in production, it could be Redis or Azure Storage or something like that. And so you can see that it's very easy to store state, and it's even easier to read state in Orleans. And so this deals with our write contention issues as well as our caching issues, because this grain is responsible for both reads and writes, and it can sequence them appropriately. Now, the add vote method is also quite simple. The main difference here is that it performs a little bit of input validation. Oops. It updates the state, and then it also writes it back to storage. So it updates the state just by adding one to the votes for the corresponding option after it's validated it. Okay, so that's the poll grain. We also mentioned that we have this user agent grain. And here's the definition of it. It's got those same three methods, slightly different definitions, because in this case, we want to be able to tell the user whether or not they've actually voted for something already when they get the poll results. And we also need to be able to identify the poll that we're talking about. And when we create a poll, we need to return its ID. But otherwise, it's very similar to that iPollGrain. So how does this look? We look at the implementation class here. So we have user agent grain. It's also a grain type, and it implements this iUser agent grain. Now, in this case, just for the purpose of the demo, I'm not actually persisting this state. All I'm going to do is just store it on the grain class itself as private member variables. So if there was a server crash, we'd lose all of this, but that's okay for now. We just don't really care. And the state that we have here is a hash set that says which polls have I created, another one that says which polls have I voted in, and then some state to make sure that we can't flood the system with requests. So we've got some throttling state, basically. And so if we look at this implementation of our first method, the one that gets the poll results, you can see first it checks to see if we're throttled. We'll have a look at that later. But then more importantly, this is how you interact with a grain. So in Orleans, you interact with a grain by first getting a reference to it. And you get a reference to it by using iGrainFactory. So we inject iGrainFactory into the constructor, and then down here we call GrainFactory getGrain of iPolGrain with that poll ID. And so Orleans will give us a reference to that poll grain. And then we can make calls on it. So we just do a simple call, get current results from the poll, and then we take those results. We can return those results back to the user, but we also want to combine those results with our current, whether or not we've voted on that poll. Create poll is similar as well, except in the create poll case, we want to check our quotas. We want to make sure that we haven't created too many polls. So we check our internal state. Have we created too many already? If we have, we tell them that they've already created enough. Otherwise, we generate a new random ID. This is not very robust because it's only 6 characters long, but even still, we generate a random ID. We get the grain corresponding to that ID. Then we call create poll on it. We record that we created a new poll and we return this ID. So it's really quite simple to implement that logic. Okay, down in the add vote implementation, it is also very similar. Instead, this time we're checking to see have we already voted, and we block people from voting twice. Otherwise, it's the same. Get the grain, make a call. It's a similar kind of pattern. And the throttling method that we're calling in each one of those methods as a very first statement, all it does is it has a kind of a linear decay sort of model that you can look at the code to try to understand how it works, but it's quite a simple, you can make X calls in Y seconds sort of thing. Okay, so we've defined all of our grains. We know how to configure Orleans. We know how to get a reference to a grain and how to call it. How do we integrate that with our Blazor application? Let's have a look at this poll class. So this is our poll razor file, and this is that UI that you saw before here. It's quite simple. It has a set of cascading if statements. This one here says, okay, if there's an error, show an error. If we're loading, show the loading screen. Otherwise, if we haven't voted, let the user vote. And finally, if they have voted, show them the results and also have these demo buttons that we saw before. But what does the implementation look like? Here's the guts of it. You can see that all we do here in our initialize method is we just asynchronously get the results using this poll service. And so if I go to the definition of this, we can see how that looks. What this does is on startup, it's going to initialize this scoped service by using the client's IP. It's going to get the corresponding user agent grain. And then each one of the methods, each one of the methods here is simply calling into that user agent grain. So it's really just a simple wrapper around the user agent grain. So there's really not much to it. And that's the entirety of the sample. And so already, even just with a few lines of code and a few different classes, we've built a quite scalable, simple polling service or simple voting service. Okay, so that was the voting app. We touched on a few features of Orleans, but there are many more. So for example, we talked about Redis persistence. We had in-memory persistence. There's all sorts of different persistence plugins, many of them provided by the community. We've also got support in Orleans for distributed ACID transactions. So this is something that we use in Azure PlayFab in order to implement in-game transactions between players. We have support for virtual stream. So this is a high throughput streaming implementation that Halo uses to compute stats after every game, and they back it by Azure Event Hubs. We have support for ephemeral timers, so they're not durable, but durable timers, which are called reminders. So if you wanted to implement something like data deletion, you could implement that using a persistent timer. So maybe if you have GDPR requirements or something like that, you can simply set a reminder for when that data needs to be deleted. And then when that timer fires, you can delete the data. So it's quite simple to do that sort of thing. Observers that we didn't really look at today, that's how those live updates were implemented. We support mutual TLS. You can deploy Orleans anywhere. Kubernetes, the new Azure container apps. Christian Spar on Twitter has already created a simple sample for how to do that, and we hope to integrate it into the repository soon. Azure App Service, we hope to provide guidance on how to deploy to App Service later in the year. You can deploy it on VMs or pretty much anywhere, any OS. It's highly customizable. There is features for all sorts of things like call filters, which you can use to implement throttling in a more simple manner. And we have great support for dotnet. So things like dependency injection you saw today, and hosting and configuration, and of course, logging. There are plenty of samples online at aka.ms/Orleans-samples. And you can see this community provided dashboard here. Some other samples for things like a text adventure game, chat room, an IoT sample, and so forth. And thank you for joining. We have a Gitter chat room at gitter.im/dotnet/Orleans. We had just started trying out Discord, so we have a Discord at aka.ms/Orleans Discord. Here's our GitHub. My Twitter alias is Ruben Bond, and at MSFT Orleans is our Orleans handle on Twitter. Thank you.
Hey, Ruben, thank you so much. I'm trying to get the questions on the stream. Hey, there we go. Perfect. So we have, I'm starting off with our dear friend Brady Gaster. It's like, hey, yeah, it's time for Ruben Bond to talk about Orleans at .NET Conf. So thank you so much for doing that with us. Here's the first question. You mentioned how well F# fits with the client-side coding of Orleans as the method call data is immutable anyhow?
Yeah, that's a good point. Thanks, Harold. Yeah, there is support for F# through a community-driven project called Orleanka, but you can use F# with Orleans itself natively even without that. And yeah, the model does, I think, work very well.
Great. Yep, I'm sure that that's the thing I love about a product and like Orleans, that it doesn't matter which language you have. Like you choose the right tool for you and apply it as necessary. All right, so here's the next question. So Jose Silva asks, Ruben, how does Orleans grains different from actors in AkaNet?
That's a very good question. So the short answer is that grains in Orleans are an implementation of something called the virtual actor model. And the virtual actor model differs from actors in Aka.net in that you saw that we never actually explicitly create a grain in Orleans. They're sort of implicitly created for you. Whereas in more traditional actors, like in Aka.net, you create the actors rather manually by saying, I want to create a grain somewhere. There are papers that talk about the specifics of this model that you can find online, or if you want to, I can link you to some.
Perfect. So let me go to we have one more question.
Yes.
There we go.
Ruben, do you recommend using Orleans in a desktop application that processes multiple images in a parallel, or is it over-engineered?
I wouldn't call it over-engineered necessarily. I think it's really a matter of taste. But I also probably wouldn't use Orleans in a desktop application for that. I would probably instead just use, say, the TPL. We've got things like for each async, right, or parallel.for each async, and all sorts of other options. So we don't really need to use Orleans just for the concurrency. But on the other hand, if you think that the model fits very well, and maybe one day you think that you might want to make it distributed, then yeah, feel free.
Yeah, and I think that's one, you bring up an excellent point at that point, that just because you're in parallel, you're also distributed. And then, like I said, there are other tools that you can use for that. But if I were to create something and that's in parallel and distributed, I just made it a lot more complicated to troubleshoot, because now I have something else that needs to be running those individual grains or that extra processing.
Yeah, ideally it shouldn't be too difficult to troubleshoot, but even still, it might be a little bit more than you need necessarily.
Right. Yeah. And you're right. It's a bit. What I was trying to say is more like the overhead, right? And at that point, it's a quid pro quo, like many things in tech. Perfect. Well, let me see if we have any more.
Do we have any more?
Yeah. Let me check here. No, we do not. No, nothing at all. So let me come over here and let me switch to.
But there may be a few more that kind of stream in slowly on Twitter. So
we've been like 10 to 15 minutes behind. So when someone's watching and halfway through the next session, someone's asking it. So please check out Twitter and actually use the hashtag .NETConf. Just search for that and then just kind of scroll backwards from latest to that, and then you'll see some questions in there. So
yeah,
no worries.
Perfect. Well, thank you so much for taking the time. We closed on a high note with you in this session. And thank you all for watching 24 hours of .NET. Actually, beyond 24 hours because we
Oh,
started.
yes.
We started with the code party yesterday at 7 a.m.
Yeah, it's like 72 hours.
72 hours of hashtag .NET, all the things, I guess.
Yeah.
But Ruben, thank you so much.
Thanks so much, Ruben.
Yep,
Thank you.
I'm gonna move you from here, and then I think we have some friends joining us.
I think we do.
that we have. So I'm gonna have to maneuver all these things.
Friends.
Yeah, friends, come on in, and then you have that.
Oh my gosh! We made it! We made
Yes.
it! Yes!
Everybody's here. So do we have something to announce, Dad?
Yes, pull up the slide deck.
Give me
Slide
1
deck.
second. Slide deck, slide deck.
There we go.
All right,
Check it.
give me 1 second.
Get it on the
Let me
screen. We got-
share. Let's see. Oop.
Oh, you're here.
Share, not stop. Yeah.
Yeah, I did share.
Oh, dude, you sure? Click.
Oh, no.
Hit enter on this one.
It's because it's
It's sharing the tab.
Yep,
Aw.
that's the
So,
gotcha.
well, okay, stop sharing and reshare.
Okay, stop sharing
How many people did
and
we
reshare.
Because we
Share
got some good
screen.
stuff to show off.
Yeah,
There we
that
go.
one.
We should hit enter on this because
Yep, I'll hit the next arrow. So give me 1
There
second.
we go.
Ta-da! And I'm just gonna go full screen.
hit the next arrow. All right, so I wanted to show off like how many viewers we had all over the world, all these different countries. Go ahead and advance the slide.
1 second.
So we had our most live viewers. Yeah, there we go. Most live viewers from the United States. Okay.
That was me in the left there.
A lot up there in that area. But check this out this year. Jeff, you want to announce the
19 hours straight watched by somebody in Uzbekistan.
that is amazing.
Oh my
That-
God.
Thank
That
you.
is
Yeah.
14, no, that's 1,147 minutes straight. Okay. Last year, I think we had a 433, but that's insane. So thank you everybody for watching and sticking with us through this amazing conference. All right, so we also want to shout out to all our fantastic speakers.
Mhm.
Obviously, this conference would be nothing without them, of course. So this is
Oh.
all
Oh,
Yay.
100%. Thank you guys,
Yep.
everybody. All right, now we have a couple prize giveaways. All right, so Dee, do you want to announce some of these swag bags? Just like
So here are and I can't read it, but look at all these
We got a lot of stuff.
prizes, and a bunch of people won all of this stuff.
all right, so we got 25 of these. So
Oh,
you
right.
get all of this stuff. 25 people get all of this stuff. All right, ready?
Yeah.
Drum roll,
okay,
please.
okay.
From the wrong screen.
There you go.
Ta-da!
All right,
Look at
swag.
that.
All right, each person will be contacted individually by
me.
each of the sponsors. They'll send you separate packages of your stuff.
Yeah,
They'll
but I'll
show
be
you-
contacting you to get your address and stuff.
All right. Well,
Congratulations.
Congratulations.
Yeah.
Now, the secret decoder challenge was new this year.
Yeah.
Okay, so you had to get the right passphrase, right? So you had to unscramble all of those things. Okay, ready?
You ready?
Yeah.
All right.
Here
So
we
all
go.
those, here you go, the
Oh,
winners.
man.
Wow.
Oh, wow.
So Teddy Lapkin, you won the DJI mini drone courtesy of Uno platform. That is
Very
the grand
nice.
prize winner. All right. And
Yeah,
Michael
look
D.
at that.
Lewis, Xbox One, courtesy of Mobilize.
There
Yeah.
we go.
All right, and check out all the rest of the great prizes. The answer was .NET loves you.
And we do.
Oh.
We do.
Aw.
Aw.
Hearts.
Hearts.
All the hearts.
Okay, guys. Next slide is what?
Yeah. Let me do this 1 second.
What?
And
Let's see what do we got.
go
What?
ahead.
What?
Oh, you can't.
Do it.
I mean, it's the wonderful thing.
Changing focus.
There we go.
Yeah,
So I wanted
there we
to
go.
I wanted to talk about this doesn't stop, right? Learning doesn't stop. We have organized help with these organizers all over the world. You know, they are running these local events in your, area, right? And if you don't see one, I
Come
Wait
on
a
in.
sec.
And,
What?
and look who just shows up
To
because
join us.
Grab
All
grab
Say
the
right.
hello,
chair,
Scott.
slide in.
Woo.
I don't think you're on the screen yet.
Yeah,
Yeah,
and
yeah,
you're
yeah.
look
Yep, I will
tall.
move this way. I'm gonna have to.
There
I have to squat here. There we go.
we go. All right.
Scott Hunter has joined us.
All right, so if you don't see an event in your area, you can organize one. We can help. You can still sign up, but we have about, I think, 70 events worldwide, and they're all starting
Next
this
week.
week. Yeah, this week.
Ours
Tomorrow.
is Saturday.
Yeah, and they run through January. So yeah, Saturday. Cool. All right, so thank you all the organizers too for helping us keep the momentum going for .NET 6. Awesome.
Perfect.
Thank you.
Can we throw
All right,
something?
and Code Magazine, like this magazine, was special edition. Like lots of team members wrote these articles and experts from the community. Go get your free online version and read
Wait,
it all.
it's top secret. Don't tell anybody. Don't tweet this. Don't share that link
Share it out.
anywhere.
Share it out. Thank you very much from all the guys at Code Focus. Thank you so much for a great magazine. So,
If I missed a session, where will I go to watch it?
so that's exactly what you will do. Next slide.
Oh.
Hold on, wait.
Sorry.
Cloud Skills Challenge is still open. That's open until December 20th. So go to akms.netconf-csc and have fun and
Complete that challenge.
complete your challenges and do it with your colleagues and show it off. There you go.
Very nice.
All right. Okay, next one. There you go. Watch all the sessions on demand on YouTube, whack.net. Okay, they're already going online. So everything from day 1 is up there already. Okay, and day 2 is coming in, and so day 3 is just completed. So we'll have everything up there for you probably by Monday. Okay, up to Caitlin.
That's right.
All right, guys, thank you so much. It's been another great conference, and we'll see you next year.
And of course, you have to end. You have to say it's never been a better time to be a .NET developer than now.
That's right.
Yeah. All right.